Hey everyone, my name is Sibtain Raza, and today I'll be presenting an overview of next generation computing. It is based entirely on the NRC and DRDC Scientometric report from 2016. This report analyzed more than 12,000 publications to understand which computing models are emerging as potential successors or complements to traditional CMOS technology. As many of you know, CMOS scaling is hitting physical, thermal, and economic limits. That means we need new approaches that can deliver faster performance, higher energy efficiency, and better parallelism. The study identified four main focus areas for deeper analysis: biocomputing, nanocomputing, spintronics, and optical or photonic computing. In this presentation, I'll walk through these major fields, highlight their strengths and challenges, and explain what the research landscape looks like globally. Why CMOS is ending. Before diving into the new technologies, it is important to understand why CMOS is reaching its end. For decades, we've relied on shrinking transistors to get faster and more efficient processors. But as we pack more transistors onto a chip, issues like leakage currents, heat generation, quantum tunneling, and manufacturer variability start to get out of control. At the same time, the cost of cutting-edge fabrication skyrockets with each new node, making it economically unsustainable. Even if the transistors could shrink further, interconnect delays, meaning the time it takes signals to travel across a chip, now dominate overall performance. At this point, simply making transistors smaller doesn't give us a meaningful speed gains anymore. Finally, modern workloads like machine learning, robotics, and advanced simulations require entirely different types of parallelism and memory behavior. All of this pushes the industry to rethink how we compute. Requirements for beyond CMOS technologies. Any technology that attempts to succeed or complement CMOS must meet very high standards. First, it needs to scale effectively at extremely small dimensions, ideally below 10 nanometers. That also means being resistant to thermal noise, variability, and defects. Energy consumption is critical. Future devices must switch using extremely low power while still operating reliably at high speed. Another requirement is compatibility. It is not realistic for the industry to throw away existing manufacturing pipelines, so new devices must integrate into some portion of the CMOS ecosystem. Finally, many emerging technologies rely on entirely different physical state variables, like electron spin, photons, molecular structures, and magnet states. These alternative mechanisms open new possibilities for efficiency and speed, but they also introduce new engineering challenges. Phase 1 findings: global research landing. In the initial phase of the study, researchers looked at over 12,000 publications and mapped out only global clusters of this activity. Quantum computing dominated the landscape, which isn't surprising given the massive investment worldwide. But the report intentionally set quantum aside to focus on less studied but equally important areas. Biocomputing formed its own large cluster, mostly isolated from others. Interestingly, neuromorphic computing, the part of biocomputing inspired by the brain, was one of the few areas that connected strongly to both spintronics and nanocomputing. Spintronics, nanocomputing, and photonic computing formed an interconnected group of technologies. These fields share common goals such as new physical phenomena to compute with lower power and high density. This cluster map helped narrow the focus to 4 promising areas for deeper analysis. Phase 2 Focus Areas. The study selected 4 specific technologies for deep analysis. These fields were chosen because they show strong publication trends, involve major international research institutions, and have the potential to disrupt the computing landscape, especially in defense applications. Biocomputing includes DNA-based computing, membrane computing, and brain-inspired architecture. Nanocomputing explores logic devices that operate at molecular or magnetic scales, such as quantum dot cellular automata. Spintronics focuses on using electron spin rather than charge, enabling non-violent memory and logic devices with extremely low standby power. Optical or photonic computing uses photons instead of electrons to achieve ultra-fast, energy-efficient processing, and it strongly overlaps the quantum optics. These 4 categories together represent the most promising avenues for next-generation architecture outside of quantum computing. Biocomputing overview and importance. Biocomputing was the largest research field identified with over 2,000 publications. This area explores how biological systems compute, adapt, and store information. Biological systems, from bacteria to human brain, are incredibly efficient. They can operate using chemical reactions, electrical spikes, complex networks, and self-organizing processes. Biocomputing includes theoretical models like membrane computing, which mimic cellular compartments. It also includes experimental approaches like DNA computing, where strands of DNA act as logic and storage elements. It includes neuromorphic hardware, which is inspired by the firing patterns and connectivity of biological neurons. What makes biocomputing exciting is that biology naturally provides massive parallelism, fault tolerance, and adaptability, qualities that traditional digital systems struggle to replicate today. Biocomputing key approaches. Let's break down the 3 main branches of biocomputing. First is membrane computing, or P-systems. These models are inspired by the compartmental structure of living cells. P-systems process information in parallel inside nested membranes. They are extremely powerful mathematically and can take complex problems like optimization and NP-hard tasks. Next is DNA, or molecular computing. Instead of using transistors, DNA computing uses biochemical reactions to encode and manipulate information. Because a single test tube can hold trillions of DNA molecules, DNA computers are capable of massive parallelism. However, challenges include error rates, slow reaction cycles, and the need for precise lab conditions. The third branch is neuromorphic computing. This field aims to build systems that mimic the neurons that synapses in the brain. Specialized hardware like memristors can simulate synaptic plasticity, the way biological neurons strengthen and weaken connections. Projects like IBMS, True North, and Spinnaker Machine in the UK, and BrainSkills in Europe show how neuromorphic systems can perform sensory processing and pattern recognition at extremely low power. Nanocomputing overview and technologies. Nanocomputing was the smallest dataset with only 71 publications, but it contains some of the most novel ideas. Quantum dot cellular automata, or QCA, represent a completely new way of computing. Instead of using current flow, QCA stores information in the arrangement of electrons within quantum dots. The electrons naturally fall into binary configurations. That means computing could occur with almost zero electrical current, drastically reducing power usage. Nanomagnetic logic is similar but uses magnetic instead of electron positions. Each magnet can point up or down, representing a 0 or 1. These magnets influence one another through magnetic fields, allowing the logic computation without traditional transistors. The biggest challenge in nanocomputing is making the switching reliable and immune to terminal noise. Clocking systems are also difficult to miniaturize. Despite this, nanocomputing offers some of the lowest energy computing concepts ever proposed. Spintronics, principles and devices. Spintronics has a medium-sized dataset with over 500 publications, and its only field showing consistent growth between 2013 to 2016. This technology uses the sign of electrons rather than just their charge. That enables devices that store information even when the power is off. One of the most important devices is the magnetic tunnel junction, which forms the basis of modern MRAM. Another major development is spin transfer torque, which allows magnetization to be flipped using spin polarized currents. Spintronics offers extremely attractive characteristics: instant on-memory, high endurance, low energy usage, and compatibility with existing CMOS manufacturing. These qualities make Spintronics one of the strongest candidates for a next-generation memory. Conclusion and future outlook. To conclude, no single technology is poised to replace CMOS entirely. Instead, the future will likely involve hybrid architectures that combine traditional processors with specialized accelerators. Biocomputing introduces powerful concepts inspired by living systems, particularly neuromorphic computing. Nanocomputing brings extremely low energy logic models though practical challenges remain significant. Spintronic appears to have the strongest near-term commercial potential, especially with the MRAM technologies. Photonic computing offers unmatched speed and energy efficiency for communication and optical logic workloads. The report recommends continued monitoring and investment across these fields, as each one represents a viable component of the future computing landscape. Thank you for listening. I hope this gives you a clear, high-level understanding of where next-generation computing is heading and how these emerging technologies may reshape the industry. Hello everyone, and welcome back to my presentation on nanocomputing. Today I'll be focusing on one specific category presented in the NRC report, nanocomputing. Within this category, I'll be highlighting two important subtopics: nanomagnetic logic and nanoscale logic gates. These two areas represent some of the most promising directions for computing technologies that may eventually complement or even replace traditional CMOS-based systems. To illustrate these ideas, I'll be referencing two research articles that were cited directly in the report. The first is a collaboration between Berkeley and Intel Corporation on a nanomagnetic logic computing architecture. The second is a Harvard and MIT RE Corporation study on a nanoelectronic finite state machine built using nanowire transistor nodes. These two studies provide concrete real-world examples of how nanoscale logic technologies could reshape computing at the device and architectural levels. What is nanocomputing? Nanocomputing refers to any computing approach that relies on nanoscale structures to perform logic or memory operations. Instead of using electrical current switching like in CMOS transistors, nanoscale devices can operate using different physical principles such as magnetic interactions, quantum effects, or charge confinement in very small structures. According to the NRC report, Nanocomputing is one of the smallest research categories, with just 71 publications, but it is also one of the most innovative and forward-looking areas. The main motivation behind nanocomputing is the pursuit of extremely low power consumption, very high density, and reliable operation at scales where CMOS can no longer function effectively. As we continue to shrink traditional electronics, we run into severe physical limits, and nanocomputing is one path toward overcoming those limits. Why nanocomputing matters. Nanocomputing matters because CMOS technology, despite decades of success, can't keep shrinking forever. When transistors become only a few nanometers wide, heat leakage, thermal noise, and quantum tunneling start to disrupt their ability to function. Nanocomputing provides ways around these limitations. Instead of relying on electrical charge, nanoscale architectures use entirely different mechanisms: magnetic states, quantum confinement, or nanoscale wires. These new mechanisms enable future computing architectures that could operate with little or no electrical current, achieving major reductions in power consumption. This makes nanocomputing especially important for fields like defense, aerospace, embedded systems, and any system where energy efficiency is critical. As computing demands continue to grow, it becomes increasingly necessary to explore approaches beyond CMOS. Subtopic 1: Nanomagnetic Logic. Nanomagnetic logic, or NML, is one of the most promising directions of nanocomputing. Instead of using transistors, NML uses tiny nanoscale magnets to logic elements, as is logic elements. Each magnet is only a few nanometers wide, and its magnetic direction represents a binary 1 or 0. These magnets communicate through dipolar magnetic fields, forming chains that allow information to move without any electrical current. That means no heat dissipation from electron flow and far lower energy requirements than CMOS. Another major advantage is that NML is naturally non-volatile. The magnets keep their orientation and therefore their data even when the system is powered off. This makes NML an appealing candidate for extremely energy efficient logic system. Article 1: Berkeley and Intel Study on NML. The first research article referenced in the NRC report is a collaboration between UC Berkeley and Intel Corporation. Their work analyzes how NML can be used to build complete computing architectures. Specifically, the study investigates how arrays of magnets can interact to form functional logic circuits. It also explores the idea of pipeline magnetic computation, where signals flow in a synchronized way across chains of magnets using global clocking fields. This research is significant because it connects the fundamental physics of nanoscale magnetism with real architectural design considerations. It shows that nanomagnetic devices aren't just theoretical. They can be organized into paths, gates, and logic structures that resemble classical circuits. Key findings from Article 1. The Berkeley and Intel study demonstrated several important findings. First, it showed that functional magnetic chains can successfully transmit information from one nanomagnet to the next. These chains form the basics of NML circuits. Second, the researchers demonstrated that NML support majority logic, which is a powerful logic operation where the output depends on the majority of the inputs. Majority gates are the foundation of many nanomagnetic logic designs. The study has also revealed that thermal stability is a major challenge. Nanoscale magnets are extremely sensitive to temperature fluctuations, which can affect their reliability. Finally, the authors propose a hybrid architecture, where CMOS electronics provide clocking and control, while NML carries out the logic operations. This hybrid approach could balance the strengths of both technologies. NML strengths and limitations. Nanomagnetic logic has several clear strengths. It uses almost no electrical currents, making it incredibly energy efficient, and it is also non-volatile. So it retains information without power. And because magnets can be packed closely, NML offers the potential for very dense, scalable designs. However, NML also faces limitations. One issue is slow switching speed compared to CMOS. Nanomagnets take more time to flip their orientation. NML is also extremely vulnerable to thermal noise, which affects reliability. Clocking and synchronization are complex as well. Magnetic domains must switch in carefully controlled sequences, and finally, NML requires highly precise fabrication. Even slight misalignment can disrupt logic propagation. Subtopic 2. Logic gates in nanocomputing. The second subtopic is nanoscale logic gates. Logic gates such as AND, OR, and NOT are the fundamental building blocks of all digital systems. In nanocomputing, these gates are rebuilt using nanoscale components such as nanowires, molecular switches, and quantum dots. These components also allow logic to be performed at extremely small dimensions. The NRC report divides nanoscale logic gates into multiple categories, including reversible logic, quantum logic, molecular logic, database logic, and nanowire transistor logic. These types of gates are essential for constructing finite state machines, digital controllers, and compact nanoscale processors. Article 2, Harvard and MIT Nano FSM Study. The second article chosen from the report is a Harvard study and MIT Corporation collaboration. This study demonstrates that a complete nanoelectronic finite state machine, or also known as FSM, can be built using nanowire transistor nodes. Finite state machines are sequential logic circuits that store information and transition between states depending on inputs. They form the backbone of digital systems like controllers, signal processors, and embedded logic. This study shows that nanoscale devices can support not only simple logic gates, but also complex digital behavior, proving that nanowire-based logic has real computational potential. Key findings from Article 2. The Harvard and MIT article produced several key results. First, the Nano FSM successfully executed state transitions using nanowire-based switching elements. This demonstrates the sequential logic is achievable at nanoscale. Second, the FSM consumes significantly less energy than a CMOS-based equivalent. This efficiency is one of the strongest advantages of nanoscale logic technologies. The design also proved to be stable and reliable, even though the devices were used extremely small. Finally, the study suggests that nanowire-based logic could be used to build larger systems such as embedded processors and specialized controllers. Challenges facing nanocomputing. Nanocomputing shows huge potential, but there are still major hurdles to overcome. Because these devices are built at a scale of just a few nanometers, even tiny fabrication errors can cause failures. The devices are also very sensitive to temperature changes, which can disrupt their behavior. Reliability is also another concern. Small variations in the physical structure of a nano device can drastically impact performance. In systems like nanomagnetic logic, clocking and synchronization must be extremely precise. Finally, integrating nanoscale devices with existing CMOS electronics remains as an engineering challenge. Overcoming these issues is essential because nanocomputing can become practical on a large scale. In summary, nanomagnetic logic and nanoscale logic gates are two very promising approaches for computing beyond CMOS. They offer benefits like energy efficiency, high density, and new physical mechanisms for performing logic. The two research articles we explored show that these technologies can support real computation from magnetic majority gates to full nanoscale finite state machines. Even though some challenges still remain, nanocomputing continues to evolve quickly and could play an important role in the next generation computing systems. Thank you guys for watching my video. I appreciate your time.